So we've been talking about cognitive load and different forms of cognitive load. And what I want to do now is a quick simulation just to give you a sense of how an extraneous cognitive load can really impact your performance, even if you know the content, even if you know what to do, even if you know um, how to perform. So let's start here. I'm going to give you a couple of math problems, and I know it's not a math class, but bear with me and try your best. So I'm going to give you an algebra equation to work with. The first problem is I want you to look at it, try to solve it as quickly as you can, and I want you to solve for A. Now, once you see the problem on the screen, you might want to pause the video so I don't give you the answer right away if you really want to experience this. And I really urge you to try to experience it yourself because you'll get a real sense for how an extraneous cognitive load can impact learning. All right, ready? Here we go. Solve it as quickly as you can. Okay, I gave you a bit of a pause there, so hopefully you've had enough time to solve it. If you solved it correctly, A in this case is -30. And if you want me to work it out, let me know and we'll look at it in the forums. But I'm going to give you a second problem now. And what I want you to do is solve this algebra problem using Roman numerals. Same rules as before. You're solving for A. Solve it as quickly as you can. Pause the video again before doing it. But what I want you to do is try to solve it in your head, and I don't want you to convert the Roman numerals into Arabic numerals. Okay? So go ahead and try to solve it as quickly as you can. Okay, so uh, hopefully you paused it and you tried your best to solve for A. If you got 13 as the answer, you are wrong. It is not 13. The answer is XIII. 13 is not in Roman numerals. So you must have converted it and then solved it. But I think the vast majority of you, hopefully all of you, if you tried this exercise, probably really experienced a much harder time in the second case than the first case. And in fact, typically when I give this problem, even to mathematics teachers, people who teach algebra, for years and years and know it inside and out, they have issues with problem number 2. I often get the wrong answer. It takes them much longer to perform it. It's a much harder task for them. But they know the algebra, they know how to solve it. They're familiar with Roman numerals. They don't use them every day, but it's something they know. The key distinction between this problem and the problem down here is that we're fluent with the Arabic numerals. We use them all the time, so our brain efficiently and automatically decodes them. We don't have to think about it. It's just automatic, very little cognitive processing needed, very low extraneous load. Down here, we don't use Roman numerals much, and even though we kind of know what they are, we don't know them fluently. We don't use them all the time, so it's a much more effortful process to decode the meaning of these Roman numerals. That's a very high extraneous load, and that makes it really hard for us to solve the problem, even though we can do it. We can solve the problem, but we perform poorly because we're being overwhelmed. So this is a quick example just to give you a sense of the impact of a high extraneous load. So what do we do about it? One of the main things we can do is to find ways to reduce that extraneous load. And in this particular case, I'll show you a quick technique that's helpful. Most of you probably already know this, but I want you to think about it from the context or from the perspective of cognitive load theory. So let's look at the use of manipulatives. If you look at the image up here, this is a picture I took on my dining room table. You'll see that there's three clementines on the right-hand side of my table. And if you assume that there's an equal number of clementines on the left-hand side, one of them we can see and some are hidden in this box. The question becomes, how many are hidden in the box? And this is a basic, very simple algebra problem. I would wager that virtually every student you work with would be able to tell you how many clementines are hidden in this box. And of course, it's 2. There's 2 in there. You can actually physically see it. So by using these physical manipulatives, we've really reduced that cognitive processing load. I don't have to abstract away what these represent. I can see what they represent. I can see what the box represents. I don't have to do a lot of mental processing and decoding. So solving the underlying problem becomes much easier for me because I've taken away a lot of that abstraction. And that's why manipulatives can be very helpful for some students, but not just any manipulative. The manipulative has to be easy for the student to process. So if you have manipulatives that are abstract and the student doesn't understand well what they mean, the manipulative isn't going to help much. So just using manipulatives isn't enough. Using manipulatives in a way that reduces the cognitive load, that's the critical piece to seeing improvements in students who are struggling with some of the math, symbolic decoding and operations decoding that a lot of students struggle with. Now, once students have developed an understanding of these simple algebraic principles using manipulatives, and you can actually go quite far with manipulatives. There are certain things that might be hard to do with manipulatives, but with some creativity and the right tools, you can teach most algebraic concepts to students using physical objects. You can then move to a representational format. So up here we can see that now we've moved from the purely physical representation to one level of abstraction. The nice thing here is there is still one-to-one correspondence with all the items here and the original object. So there's very little abstraction going on. I can still see 3 orange circles on one side and 1 orange circle and the hidden box on this side. Now there's a little bit of abstraction, but it's not a huge shift from what we worked with originally. So we can start to develop some of those skills of abstraction, and once a student is proficient at this level, we can move to the fully abstract symbolic form. In this case, I've got an algebra equation 1 plus x equals 3, which is what the oranges originally represented, and what this equation up here represents is 1 plus some unknown variable equals 3. Solve for x. X, of course, is equal to 2. But if you give this equation to a student who has a lot of anxiety around math or really struggles with numerical decoding or symbolic comprehension, this can be a very high cognitive processing load for them. And even if they're able to understand the underlying concept and solve it, the format that it's presented in can act as a barrier to their understanding.